Thank you for the introduction and for the invitation to this seminar. It's my pleasure to present our recent and ongoing work on the topic of shallow water simulations on FPGAs. Before I start with the actual content, I want to briefly introduce the system we are targeting here. So it's a PC Square, the Paderborn Center for Parallel Computing. We are operating the Noctua cluster since 2018. And in that system, in the rightmost rack, most of the system is pretty standard CPU cluster, but in the rightmost rack, there are 16 FPGA nodes. Each of those nodes contains two Intel Stratix 10 FPGAs in a Bitware 520N board. And additionally, these FPGAs are connected via a custom interconnect that allows configurable point-to-point links between all of these FPGAs. In this work that I'm going to talk about today, we are focusing on the single FPGA acceleration, and on the outlook, you will see that we are also planning to extend this to multiple FPGAs. So why is it worthwhile to look at these FPGAs as acceleration device at all? I want to briefly summarize the resources that are inside such an FPGA. And most importantly, in nowadays FPGAs are the DSP blocks, of which we have more than 5,000 available in the large Stratix 10 devices. And each of those blocks can perform a single fused multiply add operation in each cycle in single precision floating point. So double precision is more involved, is also possible, but we need at least two DSPs plus additional logic resources. Next to the DSP blocks, an important resource is a block memory, which also comes in the form of many thousands individual block RAMs. Each of them is fairly small, but it can deliver a single value with a random access pattern within the memory space of each block in each cycle. And the bit width is configurable, and 32-bit is supported, fitting the single precision floating point format, but it can also have other formats. And in additional to these coarse-grained resources, the classical ingredient of FPGAs is a logic, which are on the one hand lookup tables, which can perform any form of logic operations in a configurable way, and in between them many registers that allow to pipeline designs and hold intermediate values in state machines or in data flow approaches. As I said, in our case, this FPGA is installed inside a PCIe card, which additionally provides 4 channels of DDR4 memory as off-chip memory interface. We program these with high-level tool flows. In this case, Intel FPGA SDK for OpenCL. Recently, we also started to use one API toolkit with its FPGA add-on, but since this work was started before that, all the results I present today are using OpenCL tool flows. And now the concrete work that I'm going to talk about was presented and published at PASC this year, investigating the porting a discontinuous Galerkin shallow water model on this FPGA platform. So this code works on unstructured meshes, which is a particular challenge because it has irregular memory access during large phases of its execution. And this code is configurable in many regards, most importantly with regard to the polynomial order, which allows to change or to modify the arithmetic intensity or trade-off computation for communication and memory bandwidth in the end. This code has certain performance challenges on the CPU. In particular, it's not very well suited for vectorization because it contains many small inner loops, for example, with 3, 6, or 9 iterations, which don't fit typical SIMD vector viz very well. And as already mentioned, we have indirect and irregular memory accesses. And in the broader field of shallow water simulations, a particular challenge is strong scaling when we want to simulate very long time scales, because basically the implementation dictates the size of a time step. And if we want to not only simulate a few days or weeks, but rather years or centuries, we need to simulate a certain number of time steps. And so in this work, we wanted to investigate, can this application profit from the FPGA architecture? And so when we started off, the general idea was that, yes, this small vector parallelization is very easy on FPGAs. And also for the indirect and irregular memory access, as long as we can do it with a local on-chip memory that I talked about, this is very promising. And for strong scaling, we didn't have any idea when we started off, but now we have a quite positive answer. So why do I say this was promising? Let's recap or look at the FPGA resources again, and then think about how some OpenCL code, this is the most concrete code example that you will see throughout this presentation, is going to end up on this FPGA. And I'm not going to talk about the code structure as such, but I just want to point out that in the end, all the arithmetic operations in floating point, which are all these pink bubbles, they will be mapped physically to the DSP block. So each of those bubbles will physically get one distinct DSP block somewhere on this FPGA. And similarly, all the memory accesses, when we manage to map that to local memory, so restrict the size of the required buffers accordingly, each of those accesses will be served by one or a few of these dedicated RAM blocks, and all of that will be deterministic in performance. So that's already one advantage. And then when we look further with this unrolling, we get exactly the desired property of getting small size vectors, also with factors of 3 or 6 that are not well suited for typical CPU SIMD units. So this was the part that we hoped for would work out very well. Now let's look at the code in more detail. So the background of this code are the shallow water equations, which are derived from the Navier-Stokes equations. And in the 2D case, we have 3 unknowns to solve for. One is the elevation of free water surface, so that's waves as you see them. And the other is the horizontal velocity field, so that's the movements of waves when you look at a water surface. And all these equations are constrained by multiple parameters. For example, the bathymetric depth, which is the distance between the bottom of the seabed and the normal water surface. And there are a number of further physical constants that are involved here. So these shallow water equations are continuous equations, so we need to discretize them, and first discretize them in space, which is done by the discontinuous Galerkin formulation, which yields these 4 terms. The rightmost terms will later be translated to the element kernel. So they describe the status of the system within one triangle. Then there is some edge kernel, which operates on the numerical flux on an edge between two neighboring triangles. So we do with this C delta, we denote the discrete vector of unknowns inside one triangle. And when we look at the edges, we need the inner triangle and the neighboring triangle here according to some normal. So that's the DG formulation of the shallow water equations, and an implementation for shallow water simulations that we started with and integrated our FPGA project into is a UT-best software, where the I/O and grid management, so all the infrastructure, is still some legacy Fortran code. And the DG scheme and all the computationally intensive parts were already implemented in C before we started with the FPGA implementation. So that was first published in 2002. And a nice property of this code is that it works very well in single precision. And I already motivated that this is a good match for the DSP resources on the FPGAs. As said, this code has three different polynomial discretizations. One is piecewise constant with a single basis function. There's piecewise linear with 3 basis functions, and piecewise quadratic with 6 basis functions. And the two update terms that I pointed out on the previous slide are implemented in separate integration kernels. One is running over the edge, over the elements, sorry. And to perform these integrations, depending on the polynomial order, there are 1 to 9 quadrature points that this innermost loop iterates over. And similarly, the edge kernel runs over 1, 2, or 3 quadrature points and uses internally Lax-Friedrichs Riemann solver. So far, I talked about the discretization in space. There is corresponding time discretization in this code using Runge-Kutta integration with order 1, 2, and 3. Okay, so this was the starting point. So we just, okay, sorry, I forgot to introduce the benchmark scenario. As I already said, this code works on unstructured meshes, and this is a benchmark we used throughout the results that I'm presenting today. And you see large parts of the mesh actually look regular and well structured. But there are some areas where a finer representation is required, and this also yields to individual nodes which have more than the regular 6 edges. And this means that in the end, the data structure for this mesh is really unstructured. In addition, in this scenario, we have an OpenC boundary where tidal forcing from the OpenC comes in. We simulate for all the results that I'm going to present for 1 day with a time step size of 5 seconds, which means there are 17,000 time steps in total, which we found a useful time scale to simulate the slower and the faster designs in a reasonable amount of time. The validation of this scenario is done twofold. On the one hand, there is elevation snapshots. So every couple of time steps, the full elevation of the water surface is output and plotted later for verification. And at certain observation stations, full time series data is also logged and written out in the end. We need to restrict the output with regard to snapshots to not be bandwidth limited on the output side here. Okay, and now on to the profiling that I wanted to talk about already. So we have here the high-level structure of the code again, with the element kernel running sequentially over all elements. The edge kernel in for three types of edges, iterating over lists of edges. And then finally, the Runge-Kutta time stepping and additional minimum depth control, which is important for the correctness. And we profiled this CPU implementation. So this is a single core implementation where we see that first of all, with increasing polynomial order here from piecewise constant to piecewise quadratic, the fraction of time spent in the element kernel increases to roughly half. And so for the lower polynomial order, most time is spent in the interior edge kernel. And then for the piecewise quadratic design, this is roughly balanced. And when we look at the actual performance in gigaflops here achieved here, we see that for the different kernels, we achieve between roughly 1 and 5 gigaflops, which running on at 2.8 gigahertz on the CPU means between half and 2 operations per cycle, and that reflects exactly the challenges in using the vector units on this CPU with this code. I will keep comparing our FPGA design against this single core version because we don't have a perfectly optimized parallel version of this code. So there are actually several variants that do scale to multiple cores, but we don't achieve perfect scaling. And with all we could show, we probably don't show the best case for the CPU. So for me, an inherent assumption is that when we compare the FPGA design to the CPU execution on Noctua on this Skylake Xeon Gold, which has 20 cores, we will see some speed up, but it will be very hard to achieve this 20x acceleration using all the cores. So this is just as background to keep in mind. And now let's talk about the FPGA design process. So I will build upon what I previously motivated, but first give an overview of how the process worked out. So first, we started to extract the C code into OpenCL kernels and try to have something that is functionally correct on the FPGA without any optimizations. So this is the first result. So we compare always this single CPU reference execution time between 5 seconds and 84 seconds for piecewise constant to piecewise quadratic. And no surprise, the initial FPGA design is just functional, but a lot slower. And then we started to do basically most of what is written in the optimization guide for the Intel OpenCL SDK. So in particular, make sure that all the loops that are written there are pipelined. Performance improves, but is still not there. Then we moved on to a dataflow design, which I will talk about in the next slides. We identified some algorithmic bottlenecks there, which will be some focus of my talk today, which yielded in the improved projection data flow design, which already achieved speedups in all cases. But then we identified 2 memory bottlenecks there before we arrived at the final optimized designs, which have a speed up of up to 144x against this single core CPU reference. And now going back to this motivation, how OpenCL code ends up on the FPGA in the end. So we have several kernels that we have already seen, and each of them will be a separate block on the FPGA, occupying dedicated resources for its internal operations. And then that's what I said, following the Intel optimization guide, we made sure that all the loops are pipelined. And with additional unrolling of some inner loops, we aimed at processing 1 entire element per cycle. And to be sure not to suffer from off-chip bandwidth limitations, we already tried to provide all the unknowns from local buffers in some sort of prefetching scheme first. So that would yield to an execution model where sequentially these kernels run and write their results back to global memory, and then the next kernel executes, which leaves considerable parts of the FPGA unoccupied in every time, because we already would run one kernel at a time. And so the first data flow design aimed to improve that. And through streaming the unknowns through the individual kernels and exploiting task level parallelism, keep all the instantiated hardware occupied all or most of the time. And in order to achieve that, we also made sure to keep all unknowns in local buffers and move them around through these kernels, actually. So that idea was nice and well, but obviously it had some challenges. So here is a pseudocode of the three kernels. One is the element kernel, which I already talked about, is running over all these elements. Then we have the Runge-Kutta time stepping, which in the concrete implementation also runs over all these elements. So when we get new unknown values to be forwarded to the element kernel, then in the same sequence, the element kernel can return the update values, and the Runge-Kutta kernel can work on those. But here, when we look at the edge kernel, we have a different sequence for the loop. So here the loop runs over all the interior edges and over all land edges and OpenCL edges, which have a different sequence than the elements due to this property of the unstructured mesh, which I already motivated. And now I want to discuss that data layout in the code in some more detail. So the actual unknowns are associated to elements and sorted in an array in the order of elements. So this is, if we look at the mesh with some ordering of the elements, we can nicely loop over such a data structure. But then we have the edges, which also need the data within each element for their respective operations. And so the edge data structure is first of all a list of references into the element data structure. So for example, this is a marked edge going into element 1 and 5, and then there are some other edges going to other elements. And due to the unstructured property of this mesh, so for example, here we have from this node, we have 5 neighbors and not 6. This means that in the end, all accesses in the sequence of edges become quasi-random accesses into this element array. And when we want to loop over the edges in the order of elements, so say we want to look at all edges from element 1, there's another level of indirection mapping the edges again to the element data structure. And so this is exactly the challenge. So the element loop has nice sequential memory access, and this has random access. The edge kernel has random access, and not only random access, but also we require some serialization. So the first incarnation from the data flow design that I outlined on the previous slide roughly looks like this. For the edge kernel, we first need to receive all the element values here from the previous kernel, from the minimum depth kernel. And only when all the element indices are there, we can be sure that the iterating over the edges will yield correct references with the updated values in this element array. And then for the output phase, the same condition holds. Only when we have updated all edges and written the corresponding update values to the respective elements, for example, here and there, only when all these updates are performed, we are able to send out the results in order of elements again. And when we now plot the execution of this type of code in some type of Gantt chart, we see that here the orange phase is a phase where the edge kernel receives data in the sequence of elements. Then we have the compute phase where nothing else can actually happen. And only then, when we send out the results in the sequence of elements here, the green phase, we can overlap with the other kernels. So here, this is all other kernels, the element kernel and the Runge-Kutta time stepping and minimum depth control. They can all be pipelined and overlapped with this send loop, and also with the next iteration of the receive loop. So between these stages, we already only have small additional overheads in terms of latency. That is the latency that data needs to travel through this data path once. So the latency for the critical path of arithmetic operations. And this is comparably small compared to the loops running sequentially over all the elements. And for the edges, it's even longer because we have more edges than elements. So we have a utilization of this data path, which is below our expectation because only half of the time all the kernels are occupied. And this is what we solve through co-design on the algorithmic level and on the hardware level. And the main idea is, okay, if we want to stream the data always in the order of elements, we also need to run the edge kernel in the order of elements, which first of all would mean, okay, we need to process each edge twice. So once with this element and once with this element. So then for each element, we will process 3 edges per cycle with some redundant computation, but now tying the order to the order of elements. And if we look at the operations performed here, roughly this looks like first for each edge, we need to perform 2 projections of the unknowns to the edge and then calculate the Riemann flux. And the idea was, okay, since we run everything in the order of elements anyway, why not do the projections along with the elements, and so only do it once for each element and edge combination. And this is then the improved structure of the new element of the new edge kernel running in the sequence of elements. So first, we also need to receive all the projection data from the element kernel and the element channel. This is again an orange phase, which we need to make sure that all the input data, all the projections are valid for each edge, because this edge will look at the projection data from this element and vice versa. So all the elements need to be touched once before we can start now computing again in the sequence of elements, but running over all 3 edges per element concurrently. And this means we get a complete update value per element in each cycle, which we can stream out in the order of elements. And now we can overlap this phase. This computation and send phase of the edge kernel goes through all the other kernels, element kernel and Runge-Kutta time stepping, and overlaps with the next iteration of the receive loop. So after this pipeline is filled with after some initialization phase, we have all these kernels actually occupied and overlapping, except for the latency until the first elements are through this arithmetic data path. So that's an important improvement that we made here on the co-design aspects of the algorithm and the concrete implementation. Now I want to show some results of the final FPGA design. First, synthesis results and amounts of parallelism. So with this final improved implementation, we perform one entire element integral in the element kernel along with these projections for each element. In the edge kernel, we perform 3 edge integrals per cycle. and then one accumulation and min depth step per element per cycle. So if we sum these operations performed in these kernels up, so that's only the floating point operations, we see that, for example, for piecewise constant, there are around 100 flops to be done per element, then a couple of floating point operations for the projection, 3 times 87 operations for the edge kernel, and a few more for the further kernels, summing up to 412 operations that we ideally do in each cycle in the piecewise constant implementation, and going much higher in the piecewise quadratic implementation, more than 4,000 operations that should be performed in each cycle. And we have actually compared these results with the profiling from the CPU version, which doesn't have this projection approach. So slightly different calculation here for the edges, but summing up to a similar number of total floating point operations per elements to be performed. And now, as I said, we try to map all these arithmetic operations to the DSP resources of the design, and our synthesis results with the final resource consumption on the FPGA actually confirm that. So the 412 floating point operations in the piecewise constant design map to 457. So there's some overhead DSPs in the final design. And one interesting note is here, looking at the piecewise quadratic design, we actually map these more than 4,000 operations to less than 3,000 DSPs. That's due to the multiply accumulate capability of the DSPs, which is more efficiently exploited in the piecewise quadratic design with more work to do per element or per edge. So here we fill the FPGA in terms of arithmetic use. The logic is partially used also to do special arithmetic, but also to feed all the data, calculate addresses, and so on, which leaves one more important resource to discuss, which is block memory. So as I said, in this final design, all the data, all the unknowns, but also all the mesh data will be locally served from the block memory. And so initially we started with a design that allowed for 2,000 elements, which is sufficient for this benchmark scenario that I introduced earlier. And we saw that only 2,000 out of more than 11,000 block grams were used. So we thought, okay, probably we can support also larger meshes here, and basically fitted the maximum number of supported elements until we hit the resource limitation of the block grams. So we see that for the smaller piecewise constant design, we can fit more elements, which makes sense because in the piecewise quadratic design, we have more unknowns per element. So depending on the discretization, we can have a certain upper size of meshes support at this point. Also important to point out, on the one hand, it's good that with higher polynomial order, the resource utilization in terms of DSP increases, but a side effect that you will typically see in practice when you start to fill the FPGA, the clock frequency of the final design goes down here from 350 megahertz to just more than 200 megahertz. Maybe somewhat tweaking is possible, but it's a typical effect that we see when we try to use as many parallel resources as possible. So now the expectation is that we can perform this number of arithmetic operations per cycle. And with that, we can actually build a nice performance model. So what else do we need to take into account? This latency that I talked about. So we can actually count the number of cycles that are needed for the Bahamas benchmark. which are 1,700 cycles to process each element per cycle. And then there is these additional latency cycles in the edge and element phases that somehow limit the utilization of the instantiated hardware. And with that, we can already predict the runtime very accurately. So with this number of cycles and the given clock frequency from the synthesis results, we can see that each time step will require 6.8 microseconds. So we can perform more than 100,000 time steps per second, or more than 8 simulated days per second, which is a very nice, strong scaling result already. So speeding up the small baseline scenario instead of performing larger calculations in a similar amount of time. We validated this performance model against actual measurements. So now going back from the cycles per iteration to an occupancy term, and then predicting the flops based on the occupancy times the peak flops. That's the arithmetic operations that I showed earlier in the table. So through these equations, we predicted the floating point operations, and this is a comparison to actual measurements, and we see that the model matches the measured performance very well. So there is no more unpredictable performance coming through the memory interface. The little differences that we see are probably latencies of 1 or 2 cycles that we didn't account for correctly. We also see that we achieve this performance of up to 700 gigaflops within a power envelope of at most 80 watts in practice. Okay, so just want to recap on this FPGA optimization process again. So what I talked about mostly was this step from the first data flow design, which was limited by the structure of the loops and the requirements of first filling all the buffers before we were able to compute the next result, and the improved projection data flow, for which I illustrated that now the calculations overlap nicely. In practice, it's a bit more difficult. So when we implemented this projection data flow design, we found that we actually hit off-chip bandwidth bottlenecks for all the mesh data. The unknowns were already in local memory, but also there was some inefficiency due to port arbitration at this local memory. And we have resolved these two issues on the one hand by moving also the mesh data into local memory, and then optimizing some details of the local memory layout to make sure that there is no more port arbitration and really every arithmetic unit gets its data predictably in every cycle. And so basically this nice Gantt chart with full overlapping actually corresponds to this design where we have resolved these two more memory issues. Okay, so that was the performance discussion. Let me quickly point out the validation we performed. As I said, we have on the one hand full elevation snapshots. One of them you can see here, and it looks perfectly the same as on the CPU, and in between, while we had some bugs, we were seeing that, for example, around this small island, some artifacts would be showing up. So both the elevation snapshots seem to be correct, as well as the time series at the observation station. So here with plots from velocity and from surface elevation at station 2, comparing the CPU and FPGA versions. And so there are minor numeric differences, which is to be expected due to reordering of operations and rounding. You see the same effects when you start vectorizing the code on a CPU. And within that differences, the results are perfectly reproducible. So that's the current status that we presented at PASC, and we are not fully done with the topic yet. So first of all, you may have noticed that for the piecewise constant and piecewise linear design, the FPGA was just not full. So we are not using all the arithmetic capacity of the FPGA. And one approach we look into right now is to implement multiple full computation pipelines on a single FPGA to make use of these additional resources. And so the reason we decided to look into this direction to fill the rest of the FPGA is because once this concept works properly, we can already extend it to multiple FPGAs. Now, not only running multiple pipelines on a single FPGA, but using this direct point-to-point links, also scale over multiple pipelines on multiple FPGAs. And this is actual work in progress and looking fairly promising. Other directions to look into, so we do have a limitation in terms of meshes supported due to the bandwidth limitations. Looking forward to FPGAs with high bandwidth memory, we hope to also put some data back to off-chip memory, and with proper streaming and prefetching, or with temporal blocking, to be able to also simulate arbitrarily large meshes. We also look into further co-design improvements, in particular with regard to block structured meshes and corresponding data flow architectures. A completely different direction is looking into abstraction. So now this was a very concrete implementation that we ported to FPGA. In the long run, we might prefer to have some separation between the concrete algorithm and the architecture instantiated. So that's a long-term goal, and also looking into hybrid execution modes, coupling with other models. So for example, for the atmosphere, and maybe not executing everything on the FPGA, but allowing some fine-grained interaction with CPU or GPU resources. Okay, and with that, I want to summarize my presentation. So I have presented a data flow architecture on FPGA, where now all the kernels run in the sequence of elements. And this was enabled by the co-design between algorithm and FPGA implementation. I should have given more credit to my co-authors here, Sarah and Vadim, maybe even there, who work with the UT-Best CPU reference and were extremely helpful in achieving this result. And also thanks to Adesh, who did parts of this implementation in his master thesis, and also had great contribution to these results. And now summarizing the performance results, we achieved hundreds to thousands of operations per cycle with up to 720 gigaflops measured performance, which corresponds to a speed up of 144x over a single CPU core. And this works on small problems, which is an advantage and challenge at the same time, as already discussed. Okay. With that, I thank you for your attention, and hopefully we have some time to discuss some questions.
Thank you very much for this interesting talk. Are there any questions from the audience? Markus Walter, raise the hand.
Hold on. Yeah, there. Hi, thank you. So I was wondering, since you said, did I understand you right that the OpenCL implementation mostly uses the these P slices and the RAM, correct?
Yeah, well, you have seen that also quite some logic utilization is there. I emphasized. Okay, this one. I
Right.
emphasize the DSPs and the block RAM because they yield this predictable performance in the end, and all the arithmetic ends up on the DSPs. But you see that for the piecewise quadratic design, also a quite high number of logic slices are occupied. But from my perspective, they are infrastructure here.
Right. So my question is, what's do you know how this compares to, say, an A100 or something, performance-wise?
We didn't do any experiments on that. So my assumption is, so there are other works on discontinuous Galerkin methods on FPGA on GPUs. Generally, there are two challenges. One is if you try to implement the entire edge or element integrals on a single stream multiprocessor, you tend to run out of local memory or registers for this individual stream multipro. No, I think CUDA cores is the right term. Yeah. On the other hand, if you try to distribute this small inner loop onto the individual CUDA cores, you get a problem with getting all the parallel operations that you actually need for a GPU implementation. So there are some challenges. Definitely GPUs profit also from the high amount of off-chip memory bandwidth and the prefetching ability. I do assume that for a very large mesh, a GPU might be able to outperform the FPGA. I would be very surprised if for such a small mesh, it is possible to come anywhere near peak performance on a GPU.
All right, cool. Thank you.
Markus Fritscher is next.
Hey, actually, my question is kind of similar. I was a bit puzzled at your speed up figures. If I recall it correctly from your paper, you used some 20-core Skylake Xeon, yes. Which in theory, is that correct?
Yes, correct.
Which in theory should be somewhat 600, 800 gigaflop peak performance. Of course, there can be bandwidth issues, so one might not reach that. You stated in your paper that you only used a single core, and you didn't, and I probably missed that, did not state which optimizations you did for the CPU code. So how do you think your approach would compare to an optimized CPU version utilizing all the cores using SIMD and all that stuff?
Okay, there's two issues. So one is utilizing the multiple cores. As I hinted, we do have some similar codes running in with multi-threading, OpenMP, and some code generation approaches. So they are not one-to-one comparable. We only see roughly 10x speed up on 40 cores, so 2 sockets of this 20-core machine. It might not be the very best that is possible. That's why we left that out. So I mean, in the best case, we would hope for 40x speed up on 40 cores. I think it will be very hard to reach that goal, but so maybe somewhere between 10 and 40 should be the parallel speed up. And with regard to SIMD, so as I try to motivate, these small loops are actually hard to vectorize. People have tried this on earlier SIMD CPU architectures and not achieved great results. I cannot rule out that something better is possible than the reference results we show, but it will for sure be challenging as well. So right now, I would say, okay, give me 3 months maybe, and probably we could see a 20x speed up, mostly coming from the multi-core parallelization. For anything more, I'm not sure in how much time it can be done at all.
I've just been surprised by the figure of 100, hence the question. So thanks for the explanation.
Yeah, just a comment. I would be very cautious with that number because the baseline is obviously a non-optimized code. So this number could vary a lot depending on what you do to the CPU code. Are there any more questions? Comments? So I have a little question. What is your, as a person who dealt with FPGAs now for many years, what is your perception of the tools and the workflows required to get an algorithm ported to the FPGA? In which way has it improved? And could you attach a number to that? How many person hours are required to do such an effort as you did for this algorithm? How would it have been like 5 or 10 years ago? Can you say something about that?
Okay, let me first think about what went into this project. Probably a little bit below 1 full person year, achieving the results we presented here. Okay, where do I have the overview slide? So the nice part is the first step was fairly quick and much easier than it would have been in the past, and also much easier than we anticipated. So we were actually able to work with all the data structures, with arrays of structs and structs of arrays coming from the host, and most of it just went through the compiler fairly fine. And over time we had to optimize a lot of it to get the performance. So I think with HDL code, so traditional design approaches, many years. I cannot really say, but it's a factor of a couple of times less time, and it so if you do a traditional design approach, you need to get all the details, the baseline architecture right from the beginning. If you plan that data flow in the wrong way, you will spend months to implement that, only then to figure out in profiling, okay, we have a utilization problem here, and then you almost can start from scratch, devising a new architecture and implementing that. And this OpenCL design approach enables a much more incremental process, figuring out a concrete bottleneck and then changing only some parts of the code, which sometimes changes a lot in the generated design under the hood, but still leaving most of the functionality untouched. And I think this is the largest benefit, not only pure design time to get something running, but then to get the architecture right. And I think this is also illustrated by the results here. So if you only go half the way, you don't gain anything from this FPGA approach, but you need to get everything right. I mean, in the end, we have almost perfectly explained performance model, and apart from the shortcomings that I outlined, not fully utilizing the FPGA, there's hardly more headroom, maybe the clock frequency, but so everything needs to fall into place. And I think that's very hard to achieve with traditional design approaches for this type of code complexity.
Okay, so thank you again for the interesting talk, and goodbye, everyone. See you next time.